In computability theory, primitive recursive functions are a class of functions that are defined using primitive recursion and composition as central operations and are a strict subset of the total µ recursive functions. Primitive recursive functions form an important building block on the way to a full formalization of computability. These functions are also important in proof theory. The term was coined by Rankine Cubes par copywriter. Most of the functions normally studied in number theory are primitive recursive. For example, addition, division, factorial, exponential and the nth prime are all primitive recursive. So are many approximations to real-valued functions. In fact, it is difficult to devise a computable function that is not primitive recursive, although some are known. The set of primitive recursive functions is known as PR in computational complexity theory. Every primitive recursive function is a total recursive function. Definition: the primitive recursive functions are among the number-theoretic functions, which are functions from the natural numbers 0, 1, 2 to the natural numbers. These functions take n arguments for some natural number n and are called NR. The basic primitive recursive functions are given by these axioms: constant function, the 0 a constant function 0 is primitive recursive. Successor function, the 1 our successor function s, which returns the successor of its argument, is primitive recursive. That is, s, k, equals k plus 1. Projection function, for every n per mil 1 n and each I with 1 per mil currency e per mil currency n, the n projection function pin, which returns its ith argument, is primitive recursive. More complex primitive recursive functions can be obtained by applying the operations given by these axioms: composition given f, ak a primitive recursive function, and km a primitive recursive functions g1. Gk, the composition of f with g1. Gk, that is the mr function, is primitive recursive. Primitive recursion, given f, ak a primitive recursive function, and g, a primitive recursive function, the r function h is defined as the primitive recursion of f and g, that is the function h is primitive recursive when, and. The primitive recursive functions are the basic functions and those obtained from the basic functions by applying these operations a finite number of times. Role of the projection functions: the projection functions can be used to avoid the apparent rigidity in terms of the arity of the functions above. By using compositions with various projection functions, it is possible to pass a subset of the arguments of one function to another function. For example, if g and h are two primitive recursive functions, then is also primitive recursive. One formal definition using projection functions is converting predicates to numeric functions. In some settings it is natural to consider primitive recursive functions that take as inputs tuples that mix numbers with truth values t equals true, f equals false, or that produce truth values as outputs. This can be accomplished by identifying the truth values with numbers in any fixed manner. For example, it is common to identify the truth value t with the number 1 and the truth value f with the number 0. Once this identification has been made, the characteristic function of a set A, which literally returns 1 or 0, can be viewed as a predicate that tells whether a number is in the set A. Such an identification of predicates with numeric functions will be assumed for the remainder of this article. Computer language definition: an example of a primitive recursive programming language is one that contains basic arithmetic operators, conditionals and comparison, and bounded loops, such as the basic for loop, where there is a known or calculable upper bound to all loops. No control structures of greater generality, such as while loops or if then plus GOTO, are admitted in a primitive recursive language. Douglas Hofstadter's Bloop and Gar paragraph del, Escher, Bach is one such. Adding unbounded loops makes the language partially recursive, or Turing complete. Floop is such, as are almost all real-world computer languages. Arbitrary computer programs, or Turing machines, cannot in general be analyzed to see if they halt or not. However, all primitive recursive functions halt. This is not a contradiction. primitive recursive programs are a non-arbitrary subset of all possible programs, constructed specifically to be analyzable. Examples: most number-theoretic functions definable using recursion on a single variable are primitive recursive. Basic examples include the addition and limited subtraction functions. Addition. Intuitively, addition can be recursively defined with the rules: add 0, x equals x, add n plus 1, x equals add n, x plus 1. To fit this into a strict primitive recursive definition, define add 0, x equals p11, x, add s, n, x equals s, p23, n, add n, x, x. Here p23 is the projection function that takes 3 arguments and returns the second one. p11 is simply the identity function. Its inclusion is required by the definition of the primitive recursion operator above. It plays the role of f. The composition of s in p23, which is primitive recursive, plays the role of g. The term s, n, refers to the successor of n. Subtraction. Because primitive recursive functions use natural numbers rather than integers, and the natural numbers are not closed under subtraction, a limited subtraction function is studied in this context. This limited subtraction function sub, a, b, or baa, returns b, a if this is non-negative and returns 0 otherwise. The predecessor function acts as the opposite of the successor function and is recursively defined by the rules, pred, 0, equals 0. Pred, n plus 1, equals n. These rules can be converted into a more formal definition by primitive recursion, pred, 0, equals 0, pred, s, n equals p12, n, pred, n. The limited subtraction function is definable from the predecessor function in a manner analogous to the way addition is defined from successor, sub, 0, x, equals p11, x, sub, s, n, x, equals pred, p23, n, sub, n, x, x. Here sub, a, b, corresponds to bar a. For the sake of simplicity, the order of the arguments has been switched from the standard definition to fit the requirements of primitive recursion. This could easily be rectified using composition with suitable projections. Other primitive recursive functions include exponentiation and primality testing. Given primitive recursive functions e, f, g, and h, a function that returns the value of g when a permale currency f and the value of h otherwise is primitive recursive. Operations on integers and rational numbers, by using gar paragraph del numberings, the primitive recursive functions can be extended to operate on other objects such as integers and rational numbers. If integers are encoded by gar paragraph del numbers in a standard way, the arithmetic operations including addition, subtraction, and multiplication are all primitive recursive. Similarly, if the rationals are represented by gar paragraph del numbers, then the field operations are all primitive recursive. Relationship to recursive functions. The broader class of partial recursive functions is defined by introducing an unbounded search operator. The use of this operator may result in a partial function, that is, a relation with at most one value for each argument, but does not necessarily have any value for any argument. An equivalent definition states that a partial recursive function is one that can be computed by a Turing machine. A total recursive function is a partial recursive function that is defined for every input. Every primitive recursive function is total recursive, but not all total recursive functions are primitive recursive. The Ackermann function a, m, n, is a well-known example of a total recursive function that is not primitive recursive. There is a characterization of the primitive recursive functions as a subset of the total recursive functions using the Ackermann function. This characterization states that a function is primitive recursive if and only if there is a natural number m such that the function can be computed by a Turing machine that always halts with an a, m, n, or fewer steps, where n is the sum of the arguments of the primitive recursive function. An important property of the primitive recursive functions is that they are a recursively enumerable subset of the set of all total recursive functions. This means that there is a single computable function f, e, n, such that, for every primitive recursive function g, there is an e such that g, n, equals f, e, n, for all n, and, for every e, the function h, n, equals f, e, n, is primitive recursive. However, the primitive recursive functions are not the largest recursively enumerable set of total computable functions. Limitations: primitive recursive functions tend to correspond very closely with our intuition of what a computable function must be. Certainly the initial functions are intuitively computable, and the two operations by which one can create new primitive recursive functions are also very straightforward. However, the set of primitive recursive functions does not include every possible total computable function This can be seen with a variant of Cantor's diagonal argument. This argument provides a total computable function that is not primitive recursive. A sketch of the proof is as follows. The primitive recursive functions of one argument can be computably enumerated. This enumeration uses the definitions of the primitive recursive functions, and can be assumed to contain every definition once, even though a same function will occur many times on the list. This means that the nth definition of a primitive recursive function in this enumeration can be effectively determined from n. Indeed, if one uses some paragraph del numbering to encode definitions as numbers, then this nth definition in the list is computed by a primitive recursive function of n. Let Fn denote the unary primitive recursive function given by this definition. Now define the evaluator function f with two arguments, by f, I, j, equals phi, j. Clearly f is total and computable, since one can effectively determine the definition of phi, and being a primitive recursive function phi is itself total and computable, so phi, j, is always defined and effectively computable. However, a diagonal argument will show that the function f of two arguments is not primitive recursive. Suppose f were primitive recursive, then the unary function g defined by g, I, equals s, f, I would also be primitive recursive, as it is defined by composition from the successor function and f. But then g occurs in the enumeration, so there is some number n such that g equals fn. But now g, n, equals s, f, n equals s, fn, n equals s, g, n gives a contradiction. This argument can be applied to any class of computable functions that can be enumerated in this way, as explained in the article Machines That Always Halt. Note however that the partial computable functions can be explicitly enumerated, for instance by enumerating Turing machine encodings. Other examples of total recursive but not primitive recursive functions are known. The function that takes m to Ackermann, m, is a unary total recursive function that is not primitive recursive. The Pariser-Harrington theorem involves a total recursive function that is not primitive recursive. Because this function is motivated by Ramsey theory, it is sometimes considered more natural than the Ackermann function. The Sedan function, the Goodstein function, some common primitive recursive functions. The following examples and definitions are from Clean pages 223 to 231. Many appear with proofs. Most also appear with similar names either as proofs or as examples, in Boulos-Burgess-Jeffrey 2002 pages 63 to 70. They add number 22 the logarithm lo, x, y, or lg, x, y, depending on the exact derivation. In the following we observe that primitive recursive functions can be of four types: functions for short, number theoretic functions from 0, 1, 2 to 0, 1, 2. Predicates, from 0, 1, 2 to truth values t equals true, f equals false. Propositional connectives, from truth values t, f to truth values t, f, representing functions, from truth values t, f to 0, 1, 2. Many times a predicate requires a representing function to convert the predicate's output t, f to 0, 1 defined below. By definition a function I, x, is a representing function of the predicate p, x, if I takes only values 0 and 1 and produces 0 when p is true. In the following, the mark apostrophe, for example a, is the primitive mark meaning the successor of, usually thought of as +1, for example a +1 equals def a. The functions 16 to 21 and g are of particular interest with respect to converting primitive recursive predicates to, and extracting them from, their arithmetical form expressed as gar paragraph del numbers. Addition, a plus b, multiplication, or, b, exponentiation, add, factorial a 0 equals 1, a equals a pred, a, decrement predecessor of a defined as if a greater than 0 then a1 and nu else 0 a. Proper subtraction, aab defined as if a per million b then ab else 0. Minimum, maximum, absolute value, ab equals defined plus, sg, a, not, signum, a, if a equals 0 then sg, a, equals 1 else if a greater than 0 then sg, a, equals 0, sg, a, signum, a, if a equals 0 then sg, a, equals 0 else if a greater than 0 then sg, a, equals 1, b divides a, ab, if the remainder equals 0 then, ab, else b does not divide a evenly, remainder, the leftover if b does not divide a evenly. Also called mod, a, b, a equals b, sga, b, a, b, sg, aab, pr, a is a prime number pr, a, equals def a greater than 1 and not, exists c, 1, c, a, c a, pi, the I plus 1 st prime number, a, exponent I of pi equals def I 1/4 x, a, pix a and not, pi x a. I 1/4 x is the minimization operator described in E below, lh, a, the length, or number of non-vanishing exponents in a, or, b, given the expression of a and b as prime factors then or, b is the product's expression as prime factors, log, x, y, logarithm of x to the base y. In the following, the abbreviation x equals def xi. xn. Subscripts may be applied if the meaning requires. A function I definable explicitly from functions I and constants q1. Qn is primitive recursive in I. B, the finite sum I pound y, zi, x, y, and product iy, xi, x, y, are primitive recursive in I. C, a predicate p obtained by substituting functions I1. Im for the respective variables of a predicate q is primitive recursive in I1. Im, q. D, the following predicates are primitive recursive in q and r. Not q, x. Q or r, q, x, vr, x, q and r, q, x, and r, x, q implies r, q, x, and r, x, q is equivalent to r, q, x, a per mil r, x. E, the following predicates are primitive recursive in the predicate r. I, y, z r, x, y, hooray z denotes there exists at least one y that is less than z such that, y, z r, x, y, hooray z denotes for all y less than z it is true that, I 1/4 is z r, x, y. The operator I 1/4 is z r, x, y, is a bounded form of the so-called minimization or mu operator, defined as the least value of y less than z such that r, x, y, is true. Or z if there is no such value. F, definition by cases, the function defined thus, where q1, qm are mutually exclusive predicates shall have the value given by the first clause that applies, is primitive recursive in I1. q1, qm, I, x, equals, I1, x, if q1, x, is true. Im, x, if qm, x, is true, Im plus 1, x, otherwise. G, if I satisfies the equation. I, y, x, equals I, y, not I, y. x2. xn, x2. xn then I is primitive recursive in I. So, in a sense the knowledge of the value not I, y, x2 to n, of the course of values function is equivalent to the knowledge of the sequence of values I, 0, x2 to n, I, y1, x2 to n, of the original function. Additional primitive recursive forms. Some additional forms of recursion also define functions that are in fact primitive recursive. Definitions in these forms may be easier to find or more natural for reading or writing. Course of values recursion defines primitive recursive functions. Some forms of mutual recursion also define primitive recursive functions. The functions that can be programmed in the loop programming language are exactly the primitive recursive functions. This gives a different characterization of the power of these functions. The main limitation of the loop language, compared to a Turing-complete language, is that in the loop language the number of times that each loop will run is specified before the loop begins to run. Finitism and consistency results. The primitive recursive functions are closely related to mathematical finitism, and are used in several contexts in mathematical logic where a particularly constructive system is desired. Primitive recursive arithmetic, a formal axiom system for the natural numbers and the primitive recursive functions on them, is often used for this purpose. PRA is much weaker than Pinot arithmetic, which is not a finitistic system. Nevertheless, many results in number theory and in proof theory can be proved in PRA. For example, Gar paragraph Dell's incompleteness theorem can be formalized into PRA, giving the following theorem: if T is a theory of arithmetic satisfying certain hypotheses, with Gar paragraph Dell sentence GT, then PRA proves the implication con T, a GT. Similarly, many of the syntactic results in proof theory can be proved in PRA, which implies that there are primitive recursive functions that carry out the corresponding syntactic transformations of proofs. In proof theory and set theory, there is an interest in finitistic consistency proofs, that is, consistency proofs that themselves are finitistically acceptable. Such a proof establishes that the consistency of a theory T implies the consistency of a theory S by producing a primitive recursive function that can transform any proof of an inconsistency from S into a proof of an inconsistency from T. One sufficient condition for a consistency proof to be finitistic is the ability to formalize it in PRA. For example, many consistency results in set theory that are obtained by forcing can be recast as syntactic proofs that can be formalized in PRA. See also, course of values recursion, Czech hierarchy, machine that always halts, recursion, primitive recursive functional, double recursion, primitive recursive set function, primitive recursive ordinal function. References: Brainerd, W.S., Landweber, L.H., Theory of Computation, Wiley, ISBN 0-471-09585-0, Robert I. Saw, Recursively Enumerable Sets and Degrees, Springer Verlag, 1987. ISBN 0-387-15299-7, Stephen Kleene Introduction to Metamathematics, North Holland Publishing Company, New York, 11th reprint 1971. In Chapter 11. General Recursive Functions A Section 57, George Boulos, John Burgess, Richard Jeffrey, Computability and Logic, 4th edition, Cambridge University Press, Cambridge, UK. CFPPA 70/71. Robert I. Saw 1995 Computability and Recursion http, www.peoplecsr Chicago EduHistory Compute PDF, Daniel Severin 2008, Unary Primitive Recursive Functions, J. Symbolic Logic Volume 73, Issue 4, pp 1122 €1138 AR Ziv Project Euclid.